In this video, we walk through the solution to question number 4 from the Chapter 10 problem-solving set. So for this particular problem, we are dealing with a variety of reduction reactions. And in order to summarize the information about reductions, because you may very well see problems that are different than parts A and B here, and I want to make sure that you're ready to tackle any of those types of problems. So the generalities of what you need to know about reduction reactions are listed here at the bottom of the page. This is going to be our reduction reaction summary. We're going to use this information to solve the problems up top. And what I want you to pay attention to is that we have, in general, 3 reducing agents. We have sodium borohydride, NaBH4, lithium aluminum hydride, and we have hydrogen plus a metal catalyst. The capabilities of each of these 3 reducing agents is going to be different, and so we have to tailor the particular reducing agent to the situation that we are working with and the desired product that we aim to achieve here. So whenever you are working with an aldehyde starting material, in that aldehyde starting material, remember that we'll have a carbonyl group directly bonded to a hydrogen. You can reduce that aldehyde group very easily with any of the 3 reducing agents. And in each case, what it's going to do is bring in a hydrogen atom here and here in order to convert that carbonyl group into a primary alcohol. So we are going to see that across the board here, regardless of what reducing agent you use, you're going to get a primary alcohol all the way through there using any of these 3 reducing agents. Similarly, with a ketone, ketones are very analogous to aldehydes, and so the types of reagents that will react with them are very similar, because the only difference between aldehyde and ketone is that aldehyde has a carbon-hydrogen bond here, ketone has a carbon-carbon bond, and so same reducing agents will work. Sodium borohydride, lithium aluminum hydride, and hydrogen plus a metal catalyst will all reduce a ketone. The product of reducing a ketone is always going to be a secondary alcohol. So if your target molecule is a secondary alcohol, reduce a ketone with any of these 3 reagents. Alkenes, on the next line, are going to be totally non-reactive with the hydride donor reducing agents, the sodium borohydride and the lithium aluminum hydride. Don't think of using those to reduce an alkene. Instead, the only thing that will reduce an alkene that we've learned is the hydrogen gas and metal catalyst, and that'll reduce the alkene with a carbon-carbon double bond to an alkane that has just the carbon-carbon single bond in there. So on to the next line, an acid anion. That would be a situation where perhaps you had a carboxylic acid group and you placed it into base, and so that proton was lost here, and therefore you have an oxygen anion. That is as difficult to reduce as a carboxylic acid. And so what's going to happen is if you mix it with sodium borohydride, which is a much weaker reducing agent than lithium aluminum hydride, you're going to see no reaction. You mix it with lithium aluminum hydride and you are going to get reduction to a primary alcohol. So anytime you have acid anion or carboxylic acid and you react with lithium aluminum hydride, you're going to get a primary alcohol product. And then no reaction if you have hydrogen gas and a metal catalyst, because the acid anion is a very highly oxidized molecule with the 3 direct bonds to oxygen. Being highly oxidized means it's difficult to reduce, and so therefore the hydrogen and metal not strong enough to reduce it, nor is the sodium borohydride. Only the heavy artillery, that is the lithium aluminum hydride, is going to reduce that. Same with an ester. So an ester is going to behave analogously to a carboxylic acid or an acid anion, in that you can't reduce it with sodium borohydride, not strong enough. You can reduce it with lithium aluminum hydride to a primary alcohol, and you can't reduce it with hydrogen gas and metal. So using that information from this table, let's tackle the problems up top here. So in order to match the structures up top with the reactions down below and predict the product, we need to know what functional group we have here in part A. Indeed, that would be an ester group. We are reacting with the ester with lithium aluminum hydride followed by dilute acid. So what happens here is that the first step of this reaction with lithium aluminum hydride is going to reduce that ester group to a primary alcohol, or specifically it's going to reduce it to an oxygen anion here. So we have our 2-carbon chain here and here. That's going to be here and here in our product. And then after we add the dilute acid there at step 2, what's going to happen is the acid is going to come in and protonate that oxygen to give us our alcohol as our final product. You may be wondering as well what happened to this oxygen here and the methyl group was attached to. At a point in the mechanism, which you can review in one of the chapter 10 videos, the leaving group breaks away, and that ultimately will be released as methanol. So you could go ahead and list that as a product here as well if you want. The main thing we're generally looking for here, though, when we think about reduction of esters, is we're asking what's going to happen to this portion of the molecule. And it's always going to be the case that that leaving group, the carbon-oxygen single bond, breaks away, and this carbonyl group is reduced to the carbon-oxygen single bond there. So that's part A. Part B, we have what functional group there? It is a ketone, because we recognize we have a carbonyl directly bonded to 2 carbon atoms, making this called a ketone. Coming down to ketone on our list here, ketone, and then we come across to reaction with H2 and metal. The reaction of H2 and metal with a ketone is going to reduce that carbonyl group that's a carbon-oxygen double bond to a carbon-oxygen single bond of an alcohol. So we can go ahead and draw out our alcohol product of that reaction there. So keep in mind this reaction summary at the bottom of all these different reduction reactions is a super useful review tool. It's a super useful thing to keep in mind when we're thinking about what reagent is best for reducing organic molecules, and also when we're going through and predicting products such as we were doing in parts A and B here. So you'll want to keep these things in mind about lithium aluminum hydride being a very strong reducing agent that is able to reduce practically any carbonyl group, and sodium borohydride as being a weaker reducing agent that is able to reduce carbonyls in our less highly oxidized molecules such as aldehydes and ketones. And then hydrogen and metal similarly can reduce aldehyde and ketone groups, much like sodium borohydride. Hydrogen metal also has the property that it will reduce an alkene group to an alkane, whereas our sodium borohydride does not reduce alkenes. Only the hydrogen and metal can reduce an alkene.